Greetings. Our group is formed by Priscilla Fernandez, Karla Durán, Méndez, Monserrat Vargas, and myself, and we will talk a little bit about the field-programmable gate array. A field-programmable gate array is an integrated circuit designed to be configured by a customer or a designer after manufacturing. Its configuration is generally specified using a hardware description language. It contains an array of programmable logic blocks and a hierarchy of reconfigurable interconnects allowing blocks to be wired together. The FPGA industry started from programmable read-only memory and programmable logic devices. Altera was a manufacturer of programmable logic devices and was founded in 1983 and delivered the industry's first reprogrammable logic devices in 1984, the P300, which featured a quartz window in the package that allowed users to shine an ultraviolet lamp on the die to raise the EPROM cells that held the device configuration. On the other hand, Xilinx was an American technology and semiconductor company that primarily supplied programmable logic devices, which produced the first commercially viable FPGA in 1985, the XE2064. It had programmable gates and programmable interconnects between gates. It means the beginning of a new technology and market. The 90s were a period of rapid growth for FPGAs, both in circuit sophistication and the volume of production. They were primarily used in telecommunications and networking. Finally, companies like Microsoft have started to use FPGAs to accelerate high-performance, computationally intensive systems like the data centers that operate their Bing search engine.
Continuing with the next section, now I'm going to share how the FPGA programming is executed. First of all, to start programming an FPGA, you should choose an operating system of choice or a Windows development environment, since it can run on any software available, such as Linux, macOS, or Windows. Therefore, it offers a very complete IDE, that is the Integrated Development Environment, where you can find all the necessary tools in a single software suite. In a second step, in addition to the system, some materials you need is the FPGA chip or board and the necessary cable or programmer to connect the device to the PS and transfer the writing code to the programmer. Then, like a third step, you need to know some elements or components that this type of device contains. The first thing this have is a matrix or array of elementary components such as memory cells and or NOT gates, flip-flops, and other basic elements or blocks or digital electronics for public use. Now, as we already have talked about what is needed to program, I will continue to explain how to program the FPGA in our computers. So when you already have the program written on the PS or the computer you have, what the programmer must do is to impose the way in which these essential blocks will be grouped to form a circuit to test. That is to say that the programmer describes step by step the hardware you want to have, and then describe the logic function to perform. An example to visualize this step is to run a ALU, that is the arithmetic logic unit. If we put an example in simple words, if another is programmed in the EDA, the blocks necessary to implement this component will be linked inside the FPGA so that the clip works as an original adder. Therefore, to achieve permanent linking, it's very common to use memories or fuses. This type of materials that you want to use keeps to personal criteria. Now, if we talk about the speed of operation we want to have, this subject depends on the clock frequency on which the FPGA works. For example, one of the most basic ones that runs 50 megahertz will operate at a rate of 50 million times per second. So, if we take the example that we took later, that is the other, if we put this basic PFGA, we can have an amount of sums in a second. Like we have an amount of 50 million sums in a second. Now, as a synthesis, it is clarifying that programming at PFGA is not a programming like we all know, like in Python, something like that. It's more like a hardware description in which we use languages such as VHDL, Verilog, among others. With that programming described on a logical level, what makes the circuit to implement to finally transfer to the PFGA and have a program ready. It's very simple if you think about it. It's not like a very complicated system, but you need to know the steps and the materials that will need it. With that, I continue with the next section that is in charge of my partner.
At the end of 2005, the Fpga market has been placed in a state where there are the two producers of general purpose Fpagas that are at the head of it, and the set of other computers to different by offering Fpagas with unique capabilities. Xilinx is one of great leaders of Fpga. Altera is other great Fpga leaders. Actel has Fpagas based on reprogrammable flash technology, also for Fpgas that include flash-based signal mixers. QuickLock has fuzz-based producers programmable on time.
Now, moving on to the next point, I'm going to answer how is FPGA used. In general, it allows implementation of digital hardware, so they can be configured to able to implement different digital circuits depending on what the application needs. Actually, it has a wide variety of applications. To mention a few of them, and as you can see in the presentation, in the automotive industry, speech recognition, device drivers, military systems, high performance computing, hardware emulation systems, even in medical research equipment. And in addition, they have a notable role in the development of embedded systems thanks to their ability to initiate system software development with hardware. I mean, both at the same time. So it allows system performance simulations at a very early stage of development before the final of the system architecture. So these are some applications of the FPGA.
Similar technologies. Historically, FPGA have been slower, less energy efficient, and generally achieve less functionality and their fixed axis counterpart. A study from 2000 showed that the scene implemented on FPGA need on average 40 times as much area, draw 12 times as much dynamic power, and run at the 1/3 the speed of corresponding ASIC implementation.